This homework problem looks at a group of disc golfers, and they are comparing a couple different methods of disc golfing here. So as a group of disc golfers wants to compare two different putting techniques. In one, the player throws the disc with the forehand, just like a normal frisbee, and in the other, player uses a backhand flick to throw. So they're using two different putting techniques. One is with the forehand, one is with the backhand. To test the methods, they get 20 volunteers to throw 8 discs each from 30 feet away. A lot of numbers going on there. The 30 feet away probably is not telling us anything that's going to be needed in the actual statistics. It just kind of gives us some information about how they're doing their experiment or their study. To the 20 volunteers, that may turn out to be important. It tells us how big our sample size is here. And it says they each throw 8 discs. So I'm guessing these numbers on here will represent something of how many discs they made out of the possible 8. And you can see none of these numbers are larger than 8. Half of the volunteers are randomly assigned to one of the techniques. So half of them are randomly assigned. We do have volunteers, but because there's random assignment, I'm starting to think experiment to one of the techniques, and because it says they're assigned to one of the techniques and the rest to the other, I'm thinking I probably have two separate groups. And this happens before the throwing starts. The group wants to prove that throwing forehand will work better on average than throwing backhand. So I'm just going to mark that there is something they're trying to prove, so prove that forehand is better. And then we have our results down below. And we have a series of questions above that we're going to go through. And we'll work through these one at a time, but we might jump around if it seems like it fits. First thing is, what is the explanatory variable and what are its options or the treatment groups? The explanatory variable, the cause variable, the input variable, is whatever groups we're putting people into. And it says the two different putting methods are being compared. So the explanatory variable in this scenario is going to be the putting methods. And since we've been highlighting all that in yellow, I'll highlight that there. And its treatment options, one treatment group is going to be forehand, and the other treatment group is going to be backhand. So you're either in the forehand group or the backhand group, and you're comparing two putting techniques. B says, what is measured for each individual, or what is the response variable in this scenario? Now, what are we actually measuring? We throw the frisbee from 30 feet away, and the group wants to prove that this is going to work. Here are the results below. Now, it doesn't state it, but each of these represents how many baskets were made, and I'll make sure that gets added into the problem by the time you see it. But each of these represents how many discs were made when they putted. So the response variable is how many makes out of our 8 that they tried. So how many makes? And is that quantitative or categorical? Well, because we're asking how many times did you make it, that is going to be a quantitative variable. Let's go ahead and choose a color for that. So we have our out of 8, it's going to be quantitative. How many makes? Part C, it says, if it is quantitative, is there matched pairs or two distinct samples? We know that it is not matched pairs. It is not matched pairs, and that's because half of the volunteers are randomly assigned to one of the techniques and the rest are to the other. So no one person is repeating each of these, and there's no two people in the groups that have a special bond, like twins or siblings or something of that nature. So each of these two groups, the people are just randomly split in half to use one technique, half to use the other. So it is not matched pairs, it is two distinct samples. Part D, based on the last two responses, what type of interval or test will you perform in StatKey? Well, if we do have quantitative data and it is two distinct samples, we're going to look at the difference of two means, either a test of the difference of two means or a confidence interval of the test of two means. Jumping down to E, says what is the null hypothesis in this scenario? Use the correct symbols and use subscripts to make it clear what it means. Well, whenever we have two distinct samples, we always know that the null hypothesis represents that the two groups are equal to each other. So we have a mu, and that's going to be equal to another mu. Now we need to be able to say, okay, well, which mu is this and which mu is this? They're not the same mean. Each of these represents different populations. And so for the one, it's representing the backhand group. So you could write out the word backhand. I'm just going to abbreviate it here, BH. And then the other one is the forehand group. And the null hypothesis, whenever you're doing a hypothesis test, the null hypothesis is that the two groups, the two samples, are equal to each other. The means are equal. And you generally are trying to prove something else. So the null is not what you're trying to prove, it's just kind of the default assumption that they're independent. So then the alternative hypothesis is what we're out to prove. And it's always going to be the exact same thing. We have mu of our backhand group, we have mu of our forehand group, and we just need to decide if it's going to be a not equals test where we don't have any particular direction, or if one of these are predicted to do better. It says that the group wants to prove that throwing forehand will work better on average than throwing backhand. And if we're predicting forehand is going to be better, and we're counting it in number of makes, which means the number should be bigger, we're going to have our forehand average predicted better than our backhand average as our alternative. So we have that there. And now it says, what is the p-value of your test? This is where we need to jump into StatKey to do this. So let's go ahead and pull that up. Now we're looking to do a hypothesis test, and we said that we have two distinct groups. So we are not doing a single mean for matched pairs, we are going to do the interval or test for a difference in mean. And we're going to start with the test. Just like we wrote down, our null hypothesis up here says mu1 equals mu2, as in the two groups are equal to each other. And we're going to go in, edit our data, and clear out everything that it comes preloaded with. Going back to our problem here, we have backhand data with all of these points and forehand data with all of these points. Unfortunately, the data entry is a little bit tedious here, where you're going to have to type in variable or which group it is, comma, what the result was. So the first one would be, for example, B for backhand, comma, 2. And then, once you've entered that, B for backhand, comma, 7. And you would keep going down the line until you get all the backhands, and then you start with the forehand. So forehand, comma, 3, F, comma, 3. And we have another forehand 3, so we'd enter that one in. And you would keep doing that all the way until you got all of these entered. So it's quite a few numbers. There's 20 volunteers, so you're going to have 20 different entries. Each line in StatKey represents a different individual. So if we start out with that first one, we have B, comma, 2. And I'm going to cheat and copy and paste because I typed these out ahead of time. But you're going to get this big long list that looks something like that here. And you'll always want to leave your label value if you have this checked that you have a header row so that you don't accidentally delete your first entry. So all your data is in the system, and you can see over on the side here that your forehand group has a sample average of 5.4, your backhand group has a sample average of 3.7. The forehand group did better in the samples. However, like any samples, sampling is not perfect, which means that that difference that we see there could just be due to randomness. And that's why we're doing the hypothesis test. So we generate a whole bunch of samples. And if you look down here, our randomized sample where groups are switched, and I can explain more about how that works in a different video, but the treatment group, whether you're in the forehand or backhand group, gets randomly assigned in each of these randomization samples down here, and that's what allows you to produce this curve, this varied curve. What we want to be able to do, though, is actually run our hypothesis test. We want to see, plug in our sample mean of negative 1.7, this is the difference between our sample means here, into our curve up here. We're going to go with a left tail, not a two-tail. I'll explain that after I type it in. So I'm going to adjust this lower end to negative 1.7. And the reason that I did the left tail instead of the two-tail is because we want to make sure that we carry out our alternative hypothesis, which is that mu of forehand is greater than mu of backhand. Forehand or backhand was our x1, forehand was our x2, which is why we got a negative number here. That's why I'm going off to the left. If I were to re-enter my data, let me just show you what happens if I put the forehand group first. So I were to cut and paste and put the forehands above the backhands. Hit OK. Regenerate my data. You'll notice that my x1 minus x2 is now positive 1.7. In this case, I would do a right tail test. With the exact same alternative hypothesis, I would end up doing a right tail test. The easiest way to tell is to look at what you're trying to find. You expect forehand to be bigger, and in fact in your sample forehand is bigger. So with a positive 1.7 over on the right tail, that's the side you're going to go on. It's a little bit of an art to practice doing that, but I think with a little practice you'll be just fine. Either way, it's going to give you the same results. There's obviously going to always be a little bit of error from running different size, different numbers of samples here, but that can be expected. So going back, our question was, what is the p-value of your test? Well, once we set our value down here, a sample mean to 1.7, data as high or higher than 1.7, we have a 0.05 probability of that happening. 0.05. And of course, p-values, what do we always use to decide if it's significant or not? We say, is it greater than 0.05 or less than 0.05? And so if it's exactly 0.05, that's a little bit frustrating because well, look at that. You generate the right number of samples, all of a sudden it's just under 0.05. We always remember that 0.05 is kind of an arbitrary threshold. So to say our data is significant or not significant, in this particular problem, our data is incredibly close, so I actually probably wouldn't make a judgment. I would probably go collect more data and get a more convincing p-value. But it doesn't ask us about that. All it asks us to do is actually find the p-value, and then we move on. Is this an observational study or is this an experiment? From our random assignment here that we talked about earlier, half volunteers split into the groups randomly before you started, this is going to be an experiment. So it is an experiment. Based on this and based on your p-value, what can you conclude? If your p-value is less than 0.05, and let's go ahead and just say it's 0.049 to keep things simple. It is less than 0.05. It is an experiment. Therefore, I can say that throwing forehand causes you to do better than throwing backhand. The method that you use for throwing is the cause of you doing better because it's an experiment and because I have a significant p-value. If this was not an experiment, I would just say that people who threw forehand did better. I don't know why they did better, but they did. And if our p-value was something like 0.07 or 0.19, something that was not significant, not statistically significant, then I would simply say, you know, there's no relationship between which hand you use and how well you do. Our data doesn't really prove anything, and you don't have to worry if it's an experiment or not. Part I says, what is the estimated difference between the two groups? And do this in a 95% interval. Well, to find the estimated difference between two groups, you need to do a confidence interval. So go ahead and take your data here, and you want to copy and paste all that so you don't have to retype it, because if you did, you'd probably get a little bit cranky. So we go back after we copied and pasted our data, or copied our data, we go to the confidence interval for the difference in means. Since we came from the test, we go to the interval. We edit our data and we paste it all in. So we paste in all the data. We still have a header up here. Data has a header row. And now we can generate samples again. And you'll notice that 0 is not in the middle. The technique for generating confidence intervals is a little bit different than the technique for generating hypothesis tests or finding p-values. So with confidence intervals, I'm not looking in any particular direction. I'm just trying to get the middle 95%. And so here I have my 95%, and I get an interval between negative 3.4 and, in this case, exactly 0. Generate a few more data points and maybe that will move a little bit, but for the most part it comes up to be about that. Negative 3.4 to 0 is my 95% confidence interval. And it says interpret now the confidence interval of this difference in a sentence. What this interval is saying, and here I have backhand minus forehand going from negative 3.4 to 0. I could reverse this. I'm actually going to do that because I think it makes it a little bit easier to understand. Put my forehand data first and my backhand data second. And then run my two-tail. And this time it comes out just very slightly different. Negative 0.1 to 3.4, so pretty close. The 95% interval is calculating an interval for the difference between the means of the two groups. So that means that we are 95% confident that the difference between the average makes with forehand minus the average makes with backhand is between negative 0.1 and 3.4 makes. What does that tell us? It tells us that the one group does roughly 1.7 better. We can predict somewhere between about 0 and 3 better using your forehand than using your backhand. So that wraps up this problem. Again, we started with the types of variables we had, what types of tests we were going to do, set up a hypothesis test with our null and alternatives. We ran it in StatKey to get our p-values. We kept our data to then also get a confidence interval. Skipping back, we used whether it was an observational study or experiment in combination with our p-value to decide what we could conclude about this particular problem.